Chapter 8, we're going to be doing bonding and Lewis structures and electronegativity and a bunch of different other things about bonding. We already know the basics about bonding, that being ionic, covalent, and what types of atoms are involved with them, but we're going to go into a little bit more detail. So the first thing that we should know about is that bonds, every bond, whether it's ionic or covalent, has energy associated with it. By associated, I mean the energy required to break it. They have a force holding them together. And depending on the strength of the bond, there is an energy associated with breaking that bond. This is called the bond energy. So bond energy. We're going to be talking about bond energy when it comes to ionic and covalent bonding. And ionic bonding, you know what ionic bonding is, where pluses and minuses they attract. So an ionic compound, we're going to kind of skip that, but we'll get to this is the nitty gritty about ionic compounds. This is Coulomb's law. So Coulomb's law, well, you guys aren't in E&M physics yet, but some of you, but if you do take that, or when you do take that, you'll learn about Coulomb is a unit of charge. So Coulomb's law talks about charges and talks about ions. So it is an equation meant to calculate the energy associated with the interaction of two ions. That's very important. So this equation will be given to you, and it has two variables that depend or that change the energy associated with that bond, meaning the bond energy. And those variables are Q and R. So Q is the numerical ion charge. So this means if it's +1 and -1, you're just going to put 1 times 1. It's going to be the absolute value of them because you want this bond energy to be positive, meaning the energy required to put into the bond to break it, not the energy released from the bond breaking. Energy has to be put into it to break. So if it's +2 and -2, you'd put 2 times 2. Yeah, so then the other variable is radius, R. So R is the distance between the ion centers in nanometers. And that varies with every ion. So if you have, let's say they give you a question like this. If they say you have sodium and chlorine. Chlorine's radius is 20 nanometers. Or that's way too big. Chlorine's, they're using picometers. Chlorine's radius is 1 nanometer. And sodium's radius is 2 nanometers. So what's going to be the radius between both the nuclei? 3, right, 3. Because if you draw them, so the way they interact, they're going to be next to each other, and they're going to be pretty damn close. So, let's see, draw. There we go. What's going to be like, this one is 2. This one is 1. So the total radius is the distance between ion centers. That's going to be a total of 3. So R would equal 3 in this case, plus and a minus. Now, a lot of the questions that you're going to be getting on the exam and on the homework is going to be ranking order of bond energies. And these two factors play a huge role, whether they're the charge, magnitude, or the radius. That's why it's important to know the atomic radius trend that we learned last week. Because with that trend, you can predict which bond is going to be closer together or have more energy. So based on the equation, how does charge, is an open question, how does charge affect the bond energy? Based on the equation. Anybody? Well, in this case, you're talking about both charges. So you're talking about Q1 and Q2 as the positive and the negative. So what would? More charge or less charge? All the way around, yeah. Yeah, so let's see what the chat had to say. Directly. Yes, they're directly proportional. Good. So basically, and it makes logical sense. If you have things with more charges, a +3 and a -3, they're going to be super attracted to each other compared to a +1 and a -1. So that's where that comes from. So basically, because Q1 and Q2 are in the numerator, we want to maximize that to maximize the charge, to maximize E, which is the energy. And then for radius, since it's in the denominator, it's the opposite. The bigger the radius is between the ions, or between ion centers, the lower the bond energy is. But the scale at which, if I can say this right, but the scale at which they're different, or they affect the energy, meaning the charge and the radius, is a little bit different. So if the charge, you have two variables there, Q1 and Q2. So let's say if you went from +1, -1 to +2, -2. You're now going from 1 times 1 to 2 times 2, 1 to 4. That quadruples the energy. If you go from doubling the radius, which would weaken the interaction, weaken the bond energy, make it less, you go from 1 to 2, you're only halving the bond energy. So what I'm trying to say is the charge takes more of precedence over the radius when it comes in terms of bond energy. So the first thing you should look at when you're ranking them is the energy. The second thing you should look at is the radius, because if they have this, or it's not the energy, the charges. If you have the same charges, then it's based on the radius. If you have a bigger and a smaller one, so let's say you have this bigger charges and big radius versus small radius closer together and small charges. So you think, they both matter and they should both be kind of the same. No, the one with the bigger charges is probably going to be the stronger one, have the most bond energy, because it's Q1 times Q2. Okay, so we can use this. Yeah, whatever, use to calculate. Okay, and then bond length, we know what that means. The distance between the two atoms. So bond length changes, and really the energy associated with the bond changes with length. Not really too important, but now we're going to switch gears. So that equation could be used very easily. So there's no examples of that. Yeah, but it's a plug and chug. Okay, so then you have covalent bonding. So we talked about ionic bonding and the bonding energy associated with that. Now for covalent bonding, we have, up to this point, we really only talked about one type where you have two nonmetals that share electrons. But we have two types of covalent bonds. One of them is called nonpolar, and the other one is called polar. Now, a nonpolar covalent bond has basically an equal share of those electrons. So we talked about how the electrons are shared in a covalent bond. So we have hydrogen and hydrogen, you're going to have two electrons in there. And this gets into electron dot structure a lot. But let's say you have those two electrons. In hydrogen gas, they're going to be shared pretty equally. And imagine the bond as a tug-of-war rope. So they're going to pull on it pretty weakly because they both have weak electronegativity, but they're going to pull on it with the same strength. That means the bond will be nonpolar. Polarity, the word polarity, means there's a difference. So unequal sharing of electrons means polarity. That's important. And we can determine the polarity based on the electronegativity, which we'll talk about for the next couple slides. And when you have a polar bond, meaning an unequal sharing, that's when you have this difference in electronegativity. So we're going to talk about it more later, but I'll just write it now so you hear the term before. Difference in EN, electronegativity. And examples of polar bonds are things that have really large differences in electronegativity, such as H and F. So fluorine is actually the most electronegative atom on the periodic table. And what this means is when you have a fluorine bonded to a hydrogen, which is very not electronegative, the hydrogen is not going to want to pull the electrons, but the fluorine is really strong and really pulls them. So you're going to end up with all the electrons, instead of being in the middle, they'll be very close to the fluorine. So what this would do is it would create a partial charge. The fluorine will be partially negative and the hydrogen will be partially positive. And there's a way to predict what the electronegativity difference or the polarity number would be based on just subtracting the two. But we can talk about that more in the next couple slides. So any questions on the concept of nonpolar versus polar? So each of these, every element has an electronegativity number. If these numbers are really close together and they make a covalent bond, it's nonpolar. If they're close together or the same. If they're really different, such as fluorine and hydrogen or oxygen and hydrogen, then it's going to be polar. So here's what we mean by that. So if like in a molecule of HF, it would have partial charges. So here's for fluorine would be minus, hydrogen would be plus. Okay, so just to make sure you're alive and paying attention, what type of bond is formed when electrons are shared unequally or unequally shared? Yes, good job. Everyone got it. Good. We're so smart. Okay, so electronegativity, what does that mean? So electronegativity is the ability of an atom in a molecule to attract electrons to itself. So basically, we learned about electron affinity. It follows the same exact trend as that, meaning the elements in the top right have the highest electronegativity. So they like to not only take in electrons, but they like to pull electrons closer to themselves in covalent bonds. So that's that. That's what electronegativity is. And this equation, don't be too freaked out here. This equation just means I would take the bond energy and average the bond energies if they were by themselves, but we're not going to worry about that right now. Okay, so, oh no, please don't close. I had this problem yesterday where it was not responding, but then it came back. It's getting hot. There we go. Okay. The fans are blowing. Oh, thanks for saying slide 14. I appreciate it. Okay. So electronegativity, the way you can find the number, so every covalent bond, you can calculate the electronegativity difference between the two atoms. And these numbers will be given to you. So here's what the differences look like. Here's the chart. So like I said, you have increasing electronegativity going to the top right of the periodic table and decreasing going to the bottom left. So you notice how we've only talked about electronegativity thus far when we mentioned nonmetals. So we're talking about specifically covalent bonds. The metals also have electronegativity, but it's very, very low for most part. Gold, for some reason, is 2.4. It likes electrons. And there's a reason for that. Where is gold in terms of electron configuration and the molecular diagram? It's what is it? 3, 4, 5. It's 5d9. So it's 1 away from 5d10. It needs to fill up that last subshell. So that means it wants an electron more than the other ones do. So that's why it has a higher electronegativity. So it's still considered to be kind of low, but it's higher than the other metals because it would take in an electron more readily than the other ones because of its position in molecular diagram or orbital diagram. Okay, so keep in mind that when we talk about electronegativity and bond polarity, we're specifically talking about covalent bonds. There's no such thing as a polar ionic bond. That's not a thing. So it's just polar, nonpolar for covalence. And the way you would figure it out, let's say we had HF, that molecule we saw before. So H is 2.1, F is the highest, 4.0. So we would do 4.0 minus 2.1, the absolute value of the difference, and you would get 1.9. That's a huge difference. So that means it's very polar. Put V polar. Then if you had things like NO, NO is polar because so NO is 3.0 and then oxygen is 3.5. The difference is 0.5. That's still polar, but that's on the cusp. We consider that polar. Now, the question is, all right, what's the cutoff then? There it is. There's the cutoff. So anything generally above 0.4, we consider to be polar. But that's a loose rule. It kind of depends. Yes, Logan. So the numbers on the charts will be given in the exam. So if you were to calculate, let's say they give you an example like, which of the following bonds are more polar? Well, actually, no. You'd still, so I'll tell you. Let's talk about this. So if they gave you this on an exam, you should be able to figure it out without the numbers. The trend is equally as important as the numbers. So let's do this right now without even looking at the table, just knowing the trend. It increases going to the top right, decreases going to bottom left. And hydrogen is small. So you have hydrogen. Is that polar or non-polar? Non-polar, right? They're the same element. So it's going to have an electronegativity difference of 0. It's going to be very non-polar, the most non-polar out of all of these. So it's automatically on the bottom. OH. O is all the way to the right, top right. It's right next to hydrogen or fluorine, right? So it's pretty close. But that's going to be exactly. It's going to be very polar. Chlorine. Chlorine. Where is it with respect to oxygen? It's below it. It's below it to the right. So you might think, it's more to the right, but it's a little bit below. So that's probably going to be kind of polar too. So let's put polar for now. Then we could take out ones that we know. Let's look at HF. That's super polar, right? That's the one fluorine has the most polarity or most electronegativity. So it's going to be most. Oh wait, are they in order already? Oh no, order the following. Oh. Yeah, they're not in order. So the most polar, so you'd have from most to least, you have HF, then SH. Now, if you look at sulfur, sulfur is kind of in the middle, like it's below, well, it's right below oxygen. So what's going to be more polar, the oxygen or the sulfur with the hydrogen? What's going to be more polar? We have answers. The oxygen, good, because sulfur is below it, right? And we know the trend goes from bottom left to top right. So as you go up, the electronegativity increases. So sulfur is automatically going to be less. So I think that it would be OH, because oxygen is very polar. And then chlorine would come next, because if you want to compare chlorine to sulfur, they're on the same level, but chlorine is more closer to the right. So it's going to be a little bit more electronegative than sulfur. So it would be next, HCl, and then it would be HS, and then it would be HH. So let's take a look at that. So chlorine, so this is a tough one. So chlorine and oxygen, since they're both like kind of equal distant in that if we were to draw a straight line through the diagonal, they're kind of equidistant. But when you come to the first main group elements, the 2p elements, boron, carbon, nitrogen, oxygen, fluorine, these are a lot higher in electronegativity than the ones below it. So you see that it's kind of like a jump, and the rest of them are all pretty similar, but they still observe this trend. And if you're wondering what happened to noble gases, do you think they have any electronegativity? No, right? They're non-reactive. So they don't want to react with anything. So noble gases have 0 electronegativity, but they can still partake in covalent bonds if you force them to. All right, so the answer here, you have hydrogen would be the least, you have sulfur, then the chlorine, then the oxygen, then the fluorine. So, yay, we got it right. Cool. All right, so something else important to write down is the electronegativity difference. The difference is considered nonpolar when it's 0.4 or below. So 0.4 or below. This is when they give you the numbers. So back to, I think it was Logan's question, are they going to give you the numbers? If you need it. So if they give them to you, you're probably going to need it. Like if it says what's the polarity, or like if they're asking for this number, they're clearly going to give it to you. If they give you a couple of them to rank, they may not give it to you, but they expect you to know the trend. So at least know the trend, and then the numbers will be given. At least know, if you get the numbers, how to use them, which is to subtract them. Okay, oh, there's the answers. Whoops. Okay, without using the figure in 8.3, that's this one. Without using the numbers, predict the order of electronegativity. So I guess the answers are here already, but whatever. So oxygen's the most, then nitrogen, then carbon. Sulfur, selenium, and chlorine, they're all on the same level. Chlorine would be the highest, sulfur would be second because it's right next to it, and then selenium would be a couple over. And then silicon, germanium, and tin, they're all on the same level as well. So let's take a look where they are. So where's germanium? Oh, germanium's over here. Tin and, what would we say, silicon? Yeah, silicon. So they're going up. So we know that silicon would be the high. Actually, if you look at the numbers, they're actually the same. But based on the trend, silicon's a little bit higher. But based on the numbers, they're actually the same. That's weird. But if they ask a question like that based on the trend, that would be the right answer.
Hey, Professor.
Yes.
How you doing? I'm sorry, it's Zach. I just showed up.
It's okay. You're good. You're good.
All right, thank you. Okay,
and then you have thallium, I think, TL, and then sulfur and germanium. Where's that TL? TL's right there. And then you have germanium and what was the other one? Sulfur. Oh, so yeah, that's going to the top right. So you would see sulfur would be the highest, germanium would be the second highest, and then TL would be that's actually the same again, but in that trend, you follow the trend, is what I'm trying to say. Okay, any questions on that? On that concept? No, good? All right. Cool. Oh, that's a good one. Which of the following forms the most ionic bond with chlorine? Okay. So I don't like this question at all, because you either have ionic or not ionic. Like, it's not most ionic. I mean, I guess there is, but like, so what they're getting at here is which one has a difference in electronegativity, and the biggest difference in electronegativity with chlorine. It's going to be potassium, right? Because potassium is all the way to the left. The other ones are kind of in the middle. Phosphorus, krypton, and bromine, those are nonmetals, so they're not in the equation at all. Which of the following forms the most ionic bond with chlorine? So it's going to be a battle between potassium metal and aluminum metal. In that case, potassium is more electronegative. But if they were asking the question, Nancy, I'll mark you. I'll mark you late, but you're here, so you're good. So if they were asking the question, which of the following forms the strongest ionic bond? That's different, because the strongest is based on the bond energy, right? So out of potassium and aluminum, which one would form the strongest ionic bond with chlorine? What do you guys think? Remember the bond energy equation? Q1, Q2, right? So which pair would have bigger Qs? K and Cl or Al and Cl? We have answers. We have 4 answers. Al, good. So Al, because Al, what's the charge of Al? 3, right? +3. So if it's +3, that means Q1 is going to be 3, and chlorine, the Q is going to be 1. So that's going to be the Q1 times Q2 is going to be equal to 3. Whereas for potassium, it's going to be K is going to be 1, Cl is also 1, so it's going to be 1. Okay, good. All right. Nice. Yes, this K was corresponding to the most difference in electronegativity, not the strongest. The strongest would be Al. Okay, so when we have these polar, let's go back to, bring our minds back to covalent, right? You have polar and you have nonpolar. Bigger difference than 0.4 in electronegativity, polar. Less difference, nonpolar. So there's another name for these polar molecules, or what they have. And they all have this thing called a dipole moment. So if you were in physics, or really, yeah, physics, you'll know what this means. But basically a dipole, the Earth is a dipole. A magnet is a dipole, meaning it has two poles, positive and a negative, north and south. So the molecules can have these as well, the poles. So in a polar molecule, it's a dipole, right? Polar pole. That's where you get that polarity word from, because it forms two partially charged portions. One of them is going to be partially negative and partially positive based on where the electrons are in the bond. So whichever one has the most electronegativity in that bond is going to be the partial negative end, because it will pull the electrons closer to itself. And it's always going to be fluorine, unless fluorine is paired with another fluorine. So fluorine is the most electronegative. What about fluorine gas, F2? Is that going to be polar or nonpolar? Good, nonpolar, because even though they're both heavyweights in the electronegativity division, that's the thing, they're both heavyweights and they're both exactly the same. They're going to pull that tug of war rope at the same strength. So the electrons aren't going to go anywhere. They'll stay in the middle. So good. Yeah, so here's another look of a dipole. Here's the heat map. With like, this would be partially negative, this would be partially positive. The red indicates electron rich, the blue indicates electron poor. All right, so there's some examples. You could have also the dipole moment, or a dipole, associated with covalent bonds with more than two atoms, such as water. Water is one of the best polar solvents because it can dissolve anything or most things that have this dipole moment, meaning a difference in electron densities in the molecule. So in oxygen's case, oxygen will be really electronegative compared to the hydrogens. All the electrons from water will be pulled close to the oxygen. So then your net dipole moment would go towards the oxygen. And then the heat map would look like this. And this electrostatic, what do they call electrostatic potential diagram, this is where they figured out that the electrons actually like to hang out over here. And they like orbit, they buzz around over here because of the repulsions with everything else. So we're going to get into this and why this is important when we get into atomic shapes and molecular geometry and electron geometry later in the presentation. Okay, so some dipole moments. Yeah, so some polar bonds, or some molecules have polar bonds, but they don't have a net dipole. So you can have a bunch of polar bonds, but the entire molecule itself won't be polar. Can anyone speculate on why that's the case? So you can have polar bonds within the molecule, but the entire molecule itself not polar. Anybody? The shape. That's important. So shape. Good. And Isaiah and Daniel hit it perfectly. So shape. If they're symmetrical, then the poles from each of the polar bonds cancel out perfectly. So examples. You have CF4. Nope, I wrote 2. 4. So this is called tetrafluoromethane, or TFC. So each one of these bonds is extremely polar. You have fluorine with carbon, but you have fluorine with carbon on every side. So the pole is going to be this way, this way, this way, and this way. The carbon is going to be yanked in every direction at the same force, so nothing's going anywhere. And then CO2, same thing. CO2 is actually like this. So the dipole moment will go towards the oxygens, but the net dipole is going to be 0. And here we see that over here. So the net dipole is going to be 0. There could also be net dipoles with 3 or 4 attachments, not just 2. So I showed you with 4 with the, and here's another example, CCl4. And then here's one with SO3, and then here's one with CO2. So if you have that equal pole in every direction, basically it's going to cancel out. And this term is important. So we're going to talk about this later when we get to shapes. Tetrahedral. So let's get into right now why these 3 things are these shapes. So the first one is CO2. It's linear. They call it linear, right? Because obviously you have oxygen over here, you have a carbon over there, and then you have an oxygen over here, and it's placed linearly. The reason why it's linear is because these oxygens are both electron rich, and they have electrons, and if you put oxygen next to oxygen, when they're not, or when they're in another molecule, they're going to tend to repel each other, just like oxygens in water. So we talked about polarity. When you have water, the waters will not align like this. They won't go negative to negative. That's not a hydrogen bond. The hydrogen bonds will form when you have water going positive to negative. Positive to negative. Same thing. So these negatives want to stay as far away from each other as possible. That's why it's linear. So that's the best way to get it as far apart. Let's say you have 3 things. If you have 3 things in the mix, the farthest apart you can be is 120 degrees on a planar system. So now we'll be like, all right, what if you have 4 things? And some of you are thinking, oh, okay, if you just split it into a square, like that, or like you have one thing on this side, one thing on this side, and it's 90 degrees each. But that's not true, because remember, we're in 3 dimensions. Because we're in 3 dimensions, we now can move in the other dimension, the z-axis, which means that once these balance out in their positions, we end up with a thing called a tetrahedron. So that's where 4 points of a tetrahedron are furthest away from the center as they could possibly be. So it's kind of like in a staggered, can you guys see? Wait, is my camera's on, but like it's like kind of like you have, if you're looking at me, like 2 up, and like where my fingers meet my hand is like the central atom, and then you have 2 like this, like the other direction. So it's gonna be like opposite V's. Take 2 V's, put 2 V's in each other, and flip them. So it's like staggered. That's what a tetrahedron is. And that's geometrically the furthest distance of the 4 points that they can be, which ends up not being 90 degrees, but 109.5 degrees. So the molecules know geometry too. Okay. So for each of the following molecules, show the direction of the bond polarities and indicate which ones have a dipole moment. So when they mean dipole moment, they mean a net dipole. So for HCl, even if we didn't go over Lewis structures yet, HCl is pretty simple. Is it going to be polar or non-polar? Polar, good. Cl is pretty electronegative and H isn't. So you're going to have your dipole going this direction, and it will have a dipole moment. Cl2, polar or non-polar? Good, non-polar, because they're the same element and they're going to pull equal and oppositely. Good, and now what about SO3? And it tells you, well, what you're going to have to know later in the chapter is how to figure out the Lewis structure for SO3. But for right now, it's a planar molecule with the oxygen atoms spaced evenly around the central sulfur atom. So is that going to be polar or non-polar? Good, non-polar. Good. So HCl molecule, we talked about that already. Yeah, it's going to be polar, non-polar, non-polar. Good. All right, we get it. So which of the following is most polar without being considered ionic? This is a good one. So I like this question because they say without being considered ionic. So which one will you automatically kick out? Not C. Not D. Well, yeah, D. Yeah, D for being most, because it's not polar at all. Yes. But I was talking about the without being considered ionic part. Yeah, B. So B is ionic. It's the only one here that's ionic. But good, both of you. All right, so which one of these is going to be the most polar? It might be tough. What do you think? This one, they should give you the numbers. So you guys think E. Based on the numbers, let's see. So oxygen is 3.5 and fluorine's 4. The difference between these is only 0.5. So then it would have to be carbon oxygen. So that's what I was going to go with. Yes, good job, James. Yeah, so in that kind of question, I would expect them to give you the numbers for that. So that's why I think when I modified these slides, I put the chart down here so that you can see the numbers when solving it. Yeah. Okay, so these are some things that we've already covered in the class, but it's just good to review a little bit. I'll just say them briefly, and it's your job to really have them down already. But the goal of all of these ions when they form, and we're kind of switching from covalent to ionic now, but the goal of them is to lose or gain electrons so they end up with a noble gas configuration. It's very important. So, for example, we know that the group 1As, they lose 1 electron. The group 2A, they lose 2 electrons. The group 3A lose 3 electrons for aluminum and gallium only. Now, for the halogens, group 7A gains 1 electron, 6A gains 2, nitrogen and phosphorus gain 3, carbon likes to gain 4. So we're aware of that. And you end up with, there's some exceptions like there's actually some exceptions where bismuth likes to gain or likes to lose electrons, either 3 or 5. Don't really worry about that too much. You'll see them in the bonds, and then you'll be able to see what type of bond they are. Okay, so just as a summary, there's 3 types of bonds now. So before there was ionic and covalent. All we did was learn about a big concept of electronegativity, polarity, dipole, and now there's 3 types. There's polar covalent, non-polar covalent, and then ionic. So the key differences, automatically, if you see a metal, it's probably ionic because covalents have no metals. Then if you see 2 of the same nonmetals, definitely nonpolar. If it's anything else, you might need the numbers to see if it's below 0.4, meaning the difference is below 0.4. And if it's above 0.4, it's polar. So I see this mistake happen all the time where some students, they see something like CaO, and they do the difference, and they say, oh, Ca is only like 0.3, oxygen is 3.5. That's definitely polar, heavily polar. No way, no doubt it's not polar. But Ca is calcium. Calcium is a metal, so therefore it's ionic. Okay, chemical bonds, we get it. All right, so there's different types of bonds. There is, or for covalent. Now we're going back to covalent. So in these polar or non-polar covalents, you already saw one with CO2. I drew CO2 like this. There is single bond, double bond, and triple bond. And there's no quadruple bond, but I saw a paper last year. I actually was curious, like, was there ever a quadruple bond? It's really unstable, but they did make it. They made a carbon-carbon quadruple bond, but that's all, like, whatever. They made it for like half a second, then it like split apart. So you have double bond, triple bond. A good molecule that has triple bond would be like cyanide. Cyanide. So it's C triple bond N minus, but if you put a hydrogen there, you'll have, that's cyanic acid. Other examples, you have nitrogen gas. This is the most common example where there's a triple bond involved, and then single bonds, you know. So basically the single, double, or triple means the number of electron pairs that are bonded or that are shared in between the atoms. And a key thing is that the bond lengths shorten as you increase shared electrons. And this works along with the energy associated with them, the bond energy. So as you add more bonds, what do you think is going to happen to bond energy? Increase or decrease? As you add more. Yeah, increase. So if you add more bonds, basically it's if you're trying to fuse two things together and you're using more tape, it's going to get stronger. So that's basically what we're doing. You mean like in a triple bond, talk about each one? Yeah, we do. Not now, but we do. Yeah. So there's a sigma bond, pi bonds. Is that what you're getting at? Yes. So that's a really good question. So the question was, can we differentiate between each of the specific bonds? And yes, we can. So if you have a triple bond, say nitrogen, nitrogen, this middle one is called the sigma bond. And that's based on the sigma electrons, and they kind of hang out in the middle. Then there's pi bonds. Any additional bond is called a pi bond. This is pi bond. This is pi bond. So we learned about this in chapter 11, I think. Yeah. Yeah. Okay. So good question. All right. So now when you add more bonds, it increases the bond strength and it decreases the length, which by the equation, it makes sense, because if you make them closer together, make them stronger, it's going to be harder to break them apart. So just know that that exists. So here is a chart of the average bond energies. And you might have to use this chart on homeworks, which they may give you, or you can look it up. You look up bond energy chart and this will spit out. On exams, they're going to give you the bond energies required to solve the problem. So don't worry about that. And there's really every major bond is in there. So here's some selected bonds, and here's how we can really see the trends. If you talk about carbon-carbon bonds, a single bond has a bond length of 154. You add another one, it gets lower. Add another one, it gets lower. Sorry. And then what happens to that bond energy? It gets higher because they get closer together and it's more tape in essence. Same thing happens for the other ones. Oxygen, single and double. And then it goes up, the distance goes down, energy goes up. Same with nitrogen. So here's a good question. Why isn't there a carbon-oxygen triple bond right here? There's carbon-carbon, there's carbon-nitrogen, but no carbon-oxygen. Why do you think? Good. Not each needs, but the ones that oxygen needs. Yes, good. So carbon likes 4 bonds, so it's probably going to bond with something else. But for oxygen's sake, it only likes to have 2 bonds at most. Sometimes you can force it to have 3, but it won't be happy in doing that. Its octet rule won't be satisfied. So the way this would look is you'd have, well, I mean, sometimes the octet rule could be satisfied, but in general, oxygen likes to maintain 2, so it's an easier octet rule. You don't have to get electrons from elsewhere or move them around. Okay. So bond energy, so here's what we're going to get at. We're going to end up with equations. So I'll just go right to the equation. We're going to end up with equations, or sorry, chemical equations like this, and we're going to have to figure out the bond enthalpy. So remember, here comes enthalpy again. So we're going to have to figure out the bond enthalpy of formation of the products from the individual bond energies. And it's very simple. All you do is it's actually pretty fun. You take the bonds that are broken, meaning the energy that's required for the bonds to break, minus the bonds that are formed. Once you form bonds, energy is released. So it's going to be the energy required minus the energy released. So the best way to think about it, bonds broken minus bonds formed. And this is just sum of the number of moles times the whatever, the bond energy per mole. Yeah, so that's how you figure out, that's another way to figure out delta H. And it's weird because remember when you did delta H, that's when you had the substitute. And you mentioned products minus reactants. Do you remember that? Maybe. So products minus reactants was to calculate the reaction enthalpy, enthalpy of reaction, from the enthalpy of formation of each of the reactants and products. But those enthalpy of formations were calculated using this. So this is more fundamental from going from a straight bond level, the straight atomic level. So basically, just to reiterate, bonds broken minus bonds formed. So now we're going to solve one of these. Are they still copying? So bonds broken, sum of the bonds broken minus sum of the bonds formed. And the bonds that are broken are going to be all of the ones in the reactants, right? Because they all break apart and they reform and rearrange to make the products. So it's going to be reactants minus products instead of products minus reactants. So always think the best way to think about it, broken minus formed. Okay, so whatever, you have a table, you're going to be given a table and the table's right here. But before we get to the table, let's look at the equation. So let's go through the bonds. And I'll do the first one. I'll do the CH4. So in CH4, there's not a CH4 bond, right? It could be split apart into 4 CH bonds. Now to do this, I don't know why they taught this. They covered this before, Lewis structures, but Lewis structures are really important to know for this because you need to know, are they bonded single bond, double bond? What's the bonding order? So like CF2Cl2, is the fluorine bound to the carbon, which is bound to the chlorine? Like, how does it work? What's the bonding structure look like? So the Lewis structures is the way to determine that. But for now, I'll kind of guide you along. So let's say you had CH4 looks like this, where there's carbons in the middle and there's 4 hydrogens. And then chlorine, Cl2, is just, and there's 2 of them. So it would be take 4 of the CHs, so CH, there's 4 CH bonds in Cl and CH4, plus 2 times Cl2 is written ClCl. So each one of those bonds would be 2 times ClCl plus 2 times F bond. So this is going to be bonds broken. So you calculate that, and then you're going to subtract bonds formed. Bonds broken minus bonds formed. So in this case, CF2Cl2, it looks very similar to CH4. Carbon's always in the middle. That's a thing to know. Carbon's always in the middle. And then it would look like this. For HF, it would just look like this. And for HCl, it would look like this. So now we're going to subtract the bonds formed. So the bonds formed for the CF2Cl2 would be, there's 1 CF, 2 CF. So we're going to put 2 times CF. Put everything in parentheses to be safe, plus CCl. There's 2 CCl, 2 CCl, plus 2 from the coefficient HF. So 2 HF plus 2 HCl, like that, close parentheses. So I guarantee you, not to make fun of you, but you will make a mistake on this, because it's pretty tedious. Like you're gonna miss a bond the first time you do it. And I just want to make sure I didn't miss any. I don't think I missed any. This one's pretty simple, but you're gonna miss a bond. That's why you have to practice at it. Especially when you throw more difficult ones in there that you may not know the Lewis structure for. Or if you question whether it's a double bond or a single bond. Okay, so you do the math there, and we're not going to calculate. So does everybody understand how I got this? How I got this big thing? I did the bonds broken minus the bonds formed. Does everybody understand how I got each of those bond numbers, or bond, how I broke down the molecules to get those bonds? Question? Yes. Okay, good. Yeah. Oh, no. So, good question. So in the equation here, it says n is the number of terms. By that, it means the number of, they meant like the coefficient. You multiply it by the coefficient of each of the reactants. So, yeah. I see what you're getting at. There's 5 molecules. Yeah, so I think you end up getting the same thing. Wait, Logan, I'll get to your question in a second. So you basically, best way to think about it is whatever you're looking at, break it apart into every bond, and then just add up those bond numbers. So the way I broke it down was each molecule. CH4, there's 4 CHs, that's it. 2 Cl2, I take a Cl2, write it down, multiply by 2. Take an F2, write it down, multiply by 2. So that N was confusing, right? Number of terms, but it basically means number of molecules, like how many moles of each molecule you have. But you need so basically what that's saying is you need to factor in the coefficients when you're doing it, which we did already. Yeah. Yeah, in essence, we did that. We did, since the 4CH is 1 molecule, we did that. So 1 molecule, 2, 3 molecules, 4, 5. Yeah. Okay. So Logan's question, yes, but what would you subtract for like CH and stuff? Oh, no. So C, it's not C minus H. It's just a CH bond. So those numbers come from here. So CH would be this one, 413. HCl would be here. HF would be here. What else we got? We got a CF, a Cl, like that. And we would use those numbers. Okay, to finish, yeah, I think, well, let's finish the answer. Okay, so, let me just, yeah, I could do that. That didn't work. Here we go. No. Right, I guess all we need here. All we could use is, all we need is that. I guess I have to put that there. All right. Okay, if we can see that on the bottom, then all we have to do is do the stuff, right? So here's what I mean by do the stuff. So there's 4 CH bonds here. So it'd be 4 times the CH. CH is 413. Plus, and we can put everything in parentheses. Could we do bonds broken, big parentheses, minus bonds formed, big parentheses. Plus 2 Cl2. So the Cl bond, or the Cl-Cl bond is right here. So that's 239. So 2 times 239 plus 2 times F2. F2 is right here. 154. Big parentheses, minus bonds formed. So we have 2 CF bonds. CF is right here, 485. 2 times 485 plus 2 CCl bonds, which is right here, 339, plus 2 HFs, which is 565. Oh, times 2. Plus 2 HCl's. Also be consistent. HCl is right here, 4, 2, 7. Big parenthesis. So that's what you would calculate for your answer. Does that make sense? Yeah, okay. All right, any questions online? No? All right, cool. So they did the stuff, they did the stuff, and they got it. Okay, so here's another one. So I will give you, how about that? I'll give you like 4 minutes, 5 minutes. Do this one on your own. HH, it will be our first one. So bonds broken minus bonds formed. Bonds broken is going to be the 432 plus F2, which is going to be 154, minus 2 times our HF, which is 565. And I think you're right. That looks good. Isaiah, yep, 544. And Logan, yeah, not 42. Ah, okay. 2 of you got 42. I'm sure if that was the case, other people got 42. Did you do this? Oh, were you confused by this too? Oh, okay, yeah, so the H2 is one molecule, and the F2 is a molecule as well. So they have an HH bond and an FF bond. So that's the bonds that are going to be broken. And the ones formed are going to be the ones on the right, which is 2 times the HF bond. Yeah, so multiplying so there's only one HH and one FF. So not 2 of them. If there was 2, the 2 would be here. Okay, so let's move on. If we had H3 is not a thing, but O3 is a thing. So if we had O3, you would have, this is where we get into Lewis structures, but if you had O3, O3 is actually written like this. And the number of bonds you'd have, that's why it's very important. We didn't go to Lewis structures yet, but we're going to do that next. And it's very important to know the Lewis structures before you you do this bond energy thing, because an O3, we're going to have 2 different bond energies. We're going to have an OO double bond and an OO single bond, which those are both different. So we'd have to add them up. So whatever the Lewis structure is, you add them up. You add up the bonds that are included in it. So we'll figure that out soon. So, yep, negative 544. All right, so Lewis structures, here we go. So Lewis structures, don't really, these notes are just like whatever, but they basically tell you the arrangement of the valence electrons in the atom, in each atom of a molecule. So it's very important for determining if a molecule is stable. You can determine that. And you can, well, and you can basically, I mean, it's kind of fun, it's like a puzzle, but you can determine a lot from it. And their shape. Most importantly, you can determine the shape. So we've heard of the octet rule, meaning sometimes electrons like to have 8 electrons, or electrons like to have 8 electrons. Wow. Atoms like to have 8 electrons when they're in these covalent bonds. And keep in mind, Lewis structures are only for covalent bonds, because for ionic bonds, there's no 3-dimensional arrangement. Covalent bonds are really different in the case that they're rigid, they're more rigid. So an ionic bond, you have a plus and a minus. They're kind of like if you take 2 basketballs and smush them together. Every arrangement you can possibly put them in is identical because they're just 2 next to each other. But for covalent bonds, it's different because, I mean, if you have 2, it's the same. But if you have 3 or 4, there's different shapes and different orientations they can be in different positions. So most atoms like to partake in the octet rule, meaning when their valence electron shell is full, that's when they're happy. And that usually dictates how many bonds they have. But for things like, for some exceptions, which we'll learn the exceptions first, one of them being hydrogen, hydrogen only likes to have 2 electrons when it's bonded. So initially it has 1, but it gains the other one from 1 bond. So the moral of this slide is hydrogen likes 1 bond. That's it. Hydrogen cannot bond to more than 1 thing. That is a definite rule. The other rules that we're going to learn today, some of them can be broken, but this one can't. Okay, hydrogen 1 bond. Helium, no bonds, because its 1 s2 shell is already filled. It doesn't want anything to do with more electrons. So we're never going to see helium in a covalent bond. So it doesn't bond. Then a lot of the other elements, like the octet rule. So we'll get to that in a second, but let's talk about ones that, okay, whatever, fine. We'll talk about the octet rule. Okay, so octet rule is what most of them like to partake in, where the elements form stable molecules when surrounded by 8 electrons. These 8 electrons could either be in bonds or in lone pair electrons. So there's 2 types, all right, 2 types of electron group. And we're going to be using this term when we get into shapes a lot. Electron groups. There is lone pairs and bonded pairs. For example, if you had the nitrogen gas molecule, this is the Lewis structure of nitrogen gas. Both nitrogens are doing the octet rule because each bond represents the sharing of 2 electrons, right? So each bond is 2 electrons. So you have 3 bonds there. So 2 times 3 is 6, plus the lone pair. That's 8. So that's going to be 2. So that's going to be 8. So does that make sense? And I'm sure this won't really make sense. Just does that concept make sense that they like to have 8, hydrogen likes to have 2, and the bond numbers are different. So just think about that. Once we get into practice, it will make more sense. So here's how you do it step by step. The first step is to sum up the valence electrons from all the atoms, meaning you're going to count. You're going to figure out how many are in each atom and see how many dots should be represented in the entire molecule. So if you have, let's do CH4. We'll do CH4. So how many valence electrons are in carbon? By this point, it should be pretty quick. You should be pretty quick at this. So where is carbon? What group? 4. 4A, right? So that means it has 4. So carbon is going to have 4. And then how many valence electrons does hydrogen have? 1. Good. So it's going to be 4 plus 4 times 1 because there's 4 hydrogens. So that means a total of 8. So it just so turns out that this molecule total is going to have 8 electrons. That is not the octet rule, that the molecule has to have 8. Some molecules have 30 or 50, but this one just happens to have 8. But how are those 8? Those 8 need to be represented. So next thing is use a pair of electrons to form a bond between each pair of bound atoms. That's a really roundabout way of saying connect the dots or connect the atoms. The question is, how can you connect? Actually, you know what? I don't like these rules. I don't like number 1. I don't like 2 and 3. That's stupid. The second rule is to bond them correctly, starting with 1 bond, but then you can add more later. The question is, how do we bond them correctly, and what do I mean by that? So there are some rules when it comes to bonding, and I will write them. I will get rid of 2 and 3, and I will write my own rules. So rule number 2, so right, carbon is always central atom. If you memorize these rules, you're golden. So carbon is always going to be a central atom. If you see carbon with 4 fluorines, carbon's in the middle. Hydrogen is never going to be a central atom because hydrogen can only partake in 1 bond, right? So I'm going to put 4 bonds. This is another hard rule that carbon needs to have 4 bonds. Can't have 3, can't have 5, has to have 4. If it has 3, it's not stable. If it has 5, it's not stable. That's carbon. Let's talk about oxygen. Oxygen, I'll put likes, prefers, 2 bonds. And usually when it has those 2 bonds, has 2 lone pairs of electrons. Nitrogen. Likes 3 bonds and tends to have 1 lone pair of electrons. Then it can get weird because you have, well, let's talk about halogens first. So halogens like 1 bond. And they have 3 lone pairs. Generally, this rule can be broken. So the thing with Lewis structures, sometimes the rules can be broken, but we take it in a case-by-case basis. We want to maximize the way they the amount of bonds. We want to make as many atoms happy as possible. That's the goal. So the best way to do this is practice, practice, practice. We're going to do a bunch of examples here, and then hopefully you'll start to connect the dots a little bit, literally. So the second step is to just know this. And this is the guideline to how to arrange your molecule. So if carbon's always in the middle, we have carbon in the middle. How many bonds is it like? 4. How many hydrogens are there? 4. Okay, so clearly the only way to do that is to have each single bond to carbon, like that. And that's it. Ta-da, that's it. So there's no lone pair electrons. And we know that each bond, each of these lines, corresponds to 2 electrons because it's a bonded pair. 4 bonded pairs. 4 times 2, 8 total. And we have 8 total, and we also have carbon having 8, which makes carbon happy. Every hydrogen has 2, so that makes hydrogen happy. So everything's happy. We're all good. Any questions on that? It's a very simple one. Did everybody write down those rules or take a screenshot of it or a picture? Okay, let's do examples. First one, we'll do water. H2O. How many valence electrons? It tells you. 8. Again, it happens to be 8. We'll do ones that's not 8 later. So which one's going to be in the middle? Like, let's say you didn't know, whatever. You know, okay, so why is oxygen going to be in the middle? Right, because hydrogen can't. And oxygen, we know, likes to have 2 bonds. So it just makes sense that the 2 hydrogens that are there are going to bond to the central atom, bond to the oxygen. So it goes like that. Then, this is one way you can do it, but then it's not complete. So our hydrogens are good, but our oxygen's not. Our oxygen only has 4 electrons. And how many electrons are we missing from our total of 8? We're missing 4, right? Because there's only 2 here and 2 here. We can't make any more bonds. We can't put double bonds in between the hydrogens because the hydrogens don't want that. So we have to add these electrons as lone pairs. So we have 1 lone pair, 2 lone pair on the oxygen. How does that sound? And that's basically it. But another thing is these electrons end up repelling the carbon, or the hydrogen bonding, the oxygen hydrogen bond, to make it look like this. So this is the, if you look online, Lewis structure of water, you'll see this. It'll be kind of in a bent, it's called a bent shape. But we'll learn about that when we get to the geometry. Okay, does that make sense, kind of? Well, I want a kind of right now because there's a better way to do it, to think about it. Okay, so let's do a couple. HF. Clearly, so let's count first. Okay, let's do one that's not 8, because that's 8 again. CF, no. NH3, that's a good one. We'll do NH3. So NH3, shit, that has 8 again. CF14, or CF4. So how many electrons are in CF4? How many valence? So carbon has 4. Fluorine has, good Isaiah, 7. And it's 4 times 7, which is 28, plus 4 is 32. So we need 32 total electrons. So now, the arrangement. The arrangement, carbon's going to be in the middle. We always know that. So we put carbon in the middle, and we know our fluorines are going to be on the opposite sides, because halogens like to partake in one bond. That's what we can do. But let's say we don't write the bonds yet. Another way to think about it is just draw the elements on the paper and then fill in the dots for how many electrons they have. So it would be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then carbon is 1, 2, 3, 4. So I'll give you all a second to do that. So I like this method a little bit better. Okay. So after you do that, it becomes very apparent that carbon needs 4 bonds. To get to 8 electrons, it needs 4 more electrons. It only has 4 dots. It needs 4 more. So it's going to bond to a fluorine that needs 1 more to make this single bond. Like that. Ta-da! Then you're done. Once you could account that every element is happy. Fluorine has 8. 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 8, has 4 bonds. 4 times 2 is 8. And then you're good. Okay, does that make sense? Okay, let's do NH3. So NH3, how many electrons does it have? Nitrogen is how many? Oh, well, I said nitrogen. Sorry, I said too fast. Nitrogen has, yeah, it sounded like I said hydrogen. Nitrogen has how many? Anybody? Periodic table. You should review it. 5. Yeah, 5. So 5 plus the 3 from the hydrogens, you get 8. So now, which one's going to be in the middle? Nitrogen, because hydrogen is never in the middle. So then you're going to draw your hydrogens around it. Now we can draw our electrons. So nitrogen's going to have 1, 2, 3, 4, 5. Each of our hydrogens are going to have 1. And you can imagine single bonds are going to form because hydrogens love single bonds. So the single bonds would form. And you end up with this. And this nitrogen has 2 lone pair electrons that are not bonding to anything. And that's totally fine. You can have that. But yeah. I'll let you do that, and you can ask me any questions. Any questions? All right, we'll do a tough one now. NO plus. So this one's weird. Now, the plus makes us do something different. I know I just said that really loud for no reason, but my voice fluctuates in volume. So let's do the same thing. Nitrogen, how many electrons? 5. Oxygen, how many? Good, Isaiah. I like that you said 5 now. So nitrogen, how many? Or sorry, oxygen, how many? Yeah, 6. Now we have a positive charge. So is an electron being gained or lost? Lost. So -1. So a total of 10. 10 electrons. Okay, so now we draw it. And since it's just 2 atoms, we know they're going to be bonded next to each other. And in this case, when you have charges, when it's not, this is not conventional. When you have it not conventional, sometimes it's not the best idea to draw the dots first because you don't know where they're all going. If you draw the bonds first, we'll see what happens. So I drew one bond. I'll draw one bond at a time. So we draw one bond. We know that nitrogen, you encounter a little bit of a problem, and sometimes you have to force it. So nitrogen likes how many bonds? 3, right. Oxygen likes how many? 2. Yeah, carbon likes 4. Yeah, so on the periodic table it goes, since carbon, it goes to 4, carbon and silicon are 4. Nitrogen and phosphorus are 3. Sometimes phosphorus likes to get 5. It's weird, I know. And then oxygen and sulfur like to get 2. But sulfur can also get 4 or 6. It's weird, I know. And then all the halogens like to get 1. But that can be broken, that rule can be broken as well. Okay, so anyway, since nitrogen likes 3, we're gonna draw 3. And oxygen is not happy now. So oxygen is like, what the hell? I need more, or I need less bonds. But you can be like, be quiet, we'll still fill your octet, but you're not gonna have the amount of electrons you want. So that works, yeah. So in this case, the reason why I did this is because it gets complicated. So this is like a non-conventional one, so it gets complicated. Well, does everybody make sense why so there's many reasons why I did this. The first reason why is because both octet rules are satisfied. As long as you can get both octet rules satisfied, that's a good step. That's most likely going to be right. But someone could be like, all right, why didn't I do this? Make it double bond, 2 pairs of electrons here, and no pairs of electrons, and 1 pair of electron here. Well, what's going to happen? Nitrogen's not going to be satisfied octet rule. That would equal 10, right? 2, 4, 6, 8, 10. Yeah. So that nitrogen is not going to be a satisfied octet rule. In this case, they're both going to be satisfied octet rules. That's more stable. Even though oxygen goes 1 bond above what it likes, it's still going to be stable. So for these, it's like a puzzle, but you have to think about it. So that's why what I really try to drill down, it's very, very important to know how many valence electrons each atom has, and the bond order, meaning like what bonds to what, the connectivity, and the rules, meaning oxygen likes to have 2, nitrogen likes to have 3, phosphorus could be 3 or 5, or carbon likes 4, hydrogen's 1. Those rules are important too. Once you practice enough and get good at those rules, then doing these more difficult ones won't seem as bad. You won't have to like try to do as much funky stuff. So here's the answers for them. You see the NO plus is you can have 10 total electrons. Nitrogen is bound to the oxygen, and you want both of them to satisfy the octet rule. That's the ultimate goal, and you end up with that. So the idea is sometimes you have to force it, and sometimes you're not going to have everything to be happy. Some things exceed the octet rule, and some things don't even get to the octet rule. But we'll talk about that soon. Here's a good one. So we'll take a break soon too. Yeah, after we cover the exceptions, we'll do practice. Is there practice? Yeah, we'll do practice and then, yeah, pretty soon. Okay. So which of the following does not contain at least one double bond in the Lewis structure? So let's draw the Lewis structures for these. When you have 3 atoms, it could get complicated, or 3 elements, it could get complicated. So how many electrons total? Hydrogen, we have 2 hydrogens, so that's 2. Carbon, we have 4. Oxygen, we have 6. That's going to be 12. What's going to be in the middle? Carbon. Carbon's always in the middle. Then you're going to have hydrogens and an oxygen. Now, there's different ways you could think about it, but if I would just draw them like this, carbon's in the middle, what I can do is I can draw my dots. 1 dot on each hydrogen, 6 dots on the carbon, or on the oxygen. Okay. So next would be satisfy as many atoms as you can. Hydrogen, easy, 1 bond. We know that. Oxygen needs 2 bonds. Carbon, at this point, also needs 2 more bonds. So that means they have to go together. So I'm connecting dots here, but if you clean that up, it looks like this. And this oxygen has 2 lone pairs. So does that make sense? Kind of. Any questions about that? So it's kind of like a puzzle where there's only one way to make it work, and you have to screw around with it until you find out the way it works. Okay, so this one, the question is asking for which one does not contain at least one double bond. So A has a double bond. C2H4. So let's do this the same thing. So carbons, we have 2 carbons. 2 times 4 is 8. Plus 4 hydrogens, which is 4, equals 12. So that's 12 again. Okay, so let's do this. I see some of you have the answer already, but we just need to practice the Lewis structure. So carbons are in the middle. Now in this case, there's 2 carbons. So they're both in the middle. So we can do that. Carbon, carbon. And our hydrogens, I'll just do this. It's kind of tough to explain it, but the only way for it to work is if they're here. So let's draw our dots, and we can see why it's like that. But after trial and error, you should be able to figure this out. And that's the only way for it to possibly work. All right, so all of our dots are drawn. Now, the hydrogens, easy to satisfy them. They bond to carbons. Now, if I drew it differently and I wanted to bond these hydrogens to the same carbon, it wouldn't work because you'd end up with a CH4 molecule again, and the other carbon would be left out. So a molecule that has 2 carbons and 4 hydrogens can only be written this way. So these 2 hydrogens would have to bond to this carbon. And then the remaining, each carbon needs how many bonds left? It needs 2 more bonds, right? Because it has 2 bonds already. So a double bond would form in between the carbons. So again, it's like trial and error, and it's like a puzzle. And there's going to be no lone pairs because in this case, there's no lone pairs. Everything bonds. Lone pairs aren't a bad thing either. Some, like oxygen likes to have 2 lone pairs. Nitrogen likes to have 1 lone pair. Okay, does that make sense? Kind of. Okay, so it's not this one. CO2, we know what it looks like. It looks like this. We've seen that before. So it's not that. And the answer is C3H8. So that looks like this. You have 3 carbons in the middle, and then 1, 2, 3, 4, 5, 6, 7, 8. And that's propane. And each of these lines is a hydrogen. So that's propane. And this one does not have a double bond. So the answer is D. Okay. All right, so quickly we're going to cover the exceptions, and it's good to write these down. Boron. Boron only likes 3 bonds. And it does not, well, that's not an exception itself, but the exception is that it doesn't have any lone pairs. It's pretty electron deficient, meaning it doesn't have any extra electrons. So it has lone pairs, or it has 3 bonds like nitrogen, but no lone pairs. So a BF3 molecule would not satisfy the octet rule. An NF3 molecule will satisfy the octet rule because nitrogen also likes 3 bonds, but it will have a lone pair on its core, on the nitrogen, to make the octet rule valid, but not for boron. Okay, next rule. Sometimes sulfur could have 6. Sulfur hexafluoride is pretty damn stable, and it likes to have 6. This is more intuition to know about these. Because if you see something like this, CF6, your immediate thought should be sulfur's in the middle. Oh, professor, how do you know that? Another little nuanced rule is the atoms you have the least of, let's say you have 1 of one atom and then like 5 of the other, chances are that one's going to be in the middle. That's just conventionally the way we write it out. So that's another little nuance. And that's also true for, there's another one, PF or PCl5, which there it is, there's PCl5. But in this case, sulfur does exceed the octet rule. And that's possible. And the extra 4 electrons are held in the 3d orbital. That's possible. And it's energetically stable. So write the Lewis structure for PCl5. So we'll do this one together, and then the next, and then we're going to take a break, and you're going to have 3 examples to do. All right, so write the Lewis structure for PCl5. So which one's in the middle? P. And the Cl's are all around it. Cl, 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 Cl. Doesn't matter where you write them. Phosphorus has 5 valence electrons. Chlorine has 7. So I got to write all the dots. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Each chlorine, since they're halogens, likes to partake in 1 bond. So it's going to be simply all single bonds all around. Like so, like that. And that's PCl5. And that's what it actually looks like. But yeah, good practice. If you get good at this, you don't need to calculate the sum of the valence electrons. But as good practice, you should definitely do that on the homework. And I think since the homework doesn't have spots for you to draw these structures, it's going to ask you what's the total structure, or what's the total valence electrons, what type of bond is between one of the chlorines and the phosphorus, or it'll ask different questions that would require you in some cases to write the Lewis structure to figure it out. Okay, so there are some weird structures that exceed the octet rule and they just don't make any sense. And that are something like I3 minus. So I3 minus has 22 valence electrons, and the only way to write it is all single bonds, and there's 1 iodine in the middle that would actually have 2, 4, 6, 8, 10 electrons in the middle, or onto it. This is possible. So only this one of the iodines exceeds the octet. So here are some that exceed the octet. So we can take our 10-minute break now, since I know like we're probably not gonna finish the chapter. We might not. I might have to make you watch a video, but it's pretty easy. The rest of it's not that bad because I don't want to bore you to death. Well, we'll see. So it's 7:44. We're gonna come back at 7:54, and you're gonna write these Lewis structures. And the hint is they violate the octet rule, so you're gonna kind of force it to be together. All right, so ClF3. What's going to be in the middle? Good. And around it, you're going to have F3. So in these weird ones that violate the octet rule, you're very rarely going to have double bonds. If you're not going to have double bonds because it's going against. It's going to be unstable if you add any more electrons to an already exceeded octet atom. That adding extra double bonds or triple bonds will make it even more unstable. So you want to make it as least unstable as possible. So for chlorine's case, you're going to have 7, 1, 2, 3, 4, 5, 6, 7. Fluorine is also going to have 7. So you're going to have basically halogens binding to each other, which is, in this case, semi-stable. So you're going to have single bond, single bond, single bond. The fluorines are happy. That's good. So another little rule, not really a rule, but a preferral, is if the most electronegative atoms in the structure are satisfied octets. Because more electronegative atoms are generally more reactive. And if you have more reactive atoms that are unhappy with their octet, that's not good. That means that the molecule might be unstable. So in this case, all of our fluorines are good. And our chlorine is not good. So our chlorine has 2, 4, 6, 7, 8, 9, 10. So it's 10 electrons. Each fluorine has 8. So that's good for that. Okay, so that's what ClF3 looks like. So question. And yes, Angela, good job. So radon, I'm thinking of graphics cards. Radon is a noble gas. And it has 1, 2, 3, 4, 5, 6, 7, 8. And Cl, and since there's one of the radions and there's 2 Cls, Cl would be in the middle. Or no, radion would be in the middle, just like Angela said. And your Cls are going to be on the outside with single bonds. So that's exactly what happens. Radon ends up having 10, 2, 4, 6, 8, 10. And the chlorines are happy. And the chlorines are more electronegative. The radon is not electronegative at all. So the chlorines being satisfied is a good thing. Now, ICl4 minus. What the hell? All right, so what's going to be in the middle? I, good, I. And then good job, Angela. But you didn't draw the rest of the chlorine. I know what you mean, though. So you're going to have the chlorines bound to the iodine. So I don't have much room. So here's what it would look like. You have it'd basically be just the same thing as ClF3, but you're going to have 4 halogens as Cls on the outside and 1 halogen on the inside. So you're going to have another 10 electrons for the iodine. And then the whole thing will have a charge. Now, a good question would be like, oh, where is that charge? Where is the imbalance? So the charge is most likely going to be in the central atom for this case because the chlorines are happy. So the charge would probably be here, -1. But yeah. Okay, so any questions on that? So actually the ones that violate the octet rule, if they're like that, aren't too bad. It's just a matter of just seeing which one's the least amount. That one goes in the middle, and then you just make the other ones work with single bonds. Okay, so which molecule violates the octet rule? Just from looking at it, you should be able to figure it out. I'll give you a second. And you could type in the answer if you want. Does H2O violate it? Angela's on a roll. Nice job. So I3 violates it. Why? Because that's weird. I3, we saw that one before, right? Yeah, where it's weird. The middle iodine does not have the octet rule. Other ones we might have been confused is NO3 minus. So this one actually satisfies the octet rule. So nitrogen's in the middle. Oxygens are on all sides. Total number of electrons is going to be nitrogen has 5. There's 3 oxygens, so that's 18. And the whole thing is a -1 charge. So that means you're going to add an electron. So that's going to be 24. So what this means is you're going to have draw single bonds, and then we can fill it in. So we're going to have 2 electrons here, then 1, 2, 3, 4. So let's see what we can do. So here's a way to think. There's different ways to approach them, but so the single bonds make them 6, right? There's 2 electrons in each single bond. The nitrogen here I put 2 to give it the octet. So that's the only way for this nitrogen to have the octet, if it has these lone pairs. So that nitrogen is good. So that's going to be 8. Then if we put 9, 10, 11, 12, 13, 14, good. Oxygen's good. 15, 16, 17, 18, 19, 20. Oxygen's good. 21, 22, 23, 24, 25, 26. That's too many. What do we do? So here's what we have to do. There's another place where we can put these electrons. We can put a bond here, and then we can get rid of these electrons. And we can put bonds in multiple places to get rid of lone pair electrons. And that, you can still have the octet rule, but that changes the balance a little bit. So doing that, what happens is instead of having 2 electrons over here and 2 over here, we end up sharing those 2. So that 24 is our new number. So let's double check that. We have 8 in the bonds, then 1, 2, that's 10, 12, 14, 16, 18, 20, 22, 24. And the whole thing is -1. Little weird, but does that make sense? Kind of. So it's kind of like plugging in the dots to see what works. If you end up with that's why it's important to, I know I'm all over the place, but that's why it's important to calculate how many electrons you need to have, how many dots you need to end up with, 24 in this case. So if I were to just draw single bonds and then just put all the dots, you'd see that you'd run out of dots. So some of those dots have to be converted to bonds to save electrons. And there's one way to do that that satisfies the octet rule for this case. And that's this one. Make sense? Kind of? Okay. Any questions? I understand it now. Okay, good, good. Okay, so again, practice makes perfect. All right, resonance. So resonance, we can talk about it. In orgo, you talk about it like crazy, but here's resonance in a nutshell. For something like that NO3 minus molecule, you notice how I put the double bond on this oxygen. A question could be, why on that one? Why does it have to be on that one? Why can't it be on the other ones? And the answer is, it is exactly the same molecule if it is on either one. That's what resonance is. The electrons could actually jump from one to the other, or you can rotate the molecule and it looks exactly the same. As it is exactly the same no matter how you rotate it. So that's what resonance is. And we have this double arrow, meaning that it can go from this structure to this structure, where they're exactly the same thing. So that's what resonance means. All right, so the next thing is molecular shape. And then what's after molecular shape? That's basically it. Yeah, all right. Okay. So, any questions? So now's a good time to stop and ask questions about Lewis structures. Any questions about Lewis structures at all? Like, go back to your notes. Let's see if there's any ones you weren't sure of how we found them out. Mm-hmm. 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 Well, you're not adding up all of those. So you're not adding it up like that. So the question was, wait, bonds and electrons have to be illustrated to equal. Yes. So Logan, that's a good way of saying it. So the bonds and the electrons have to be illustrated to equal the total number of electrons. Yes. So you need to add up everything in the molecule. Don't look it up. Don't look at it as each individual atom because they're redundant. Because when they're in the bonds, they count for both. So in this case, we'll do this one together. So for the number here, it would be all the dots, which would be 6 for each chlorine. So 6 times 5, which is 30, plus the bonds, which are 5 bonds. 5 times 2 is 10. So 30 plus 10, 40. Okay, so now the next part and the last part of class, what we're going to do is we're going to take this idea of Lewis structures, and I know you just learned it today, but let's say you're good at it and you know how to figure out all of them. We're going to try to figure out, based on the Lewis structure, what is the molecular shape of the molecule. So 3-dimensional shape. And there's actually 2 ways to categorize the 3-dimensional shape. One of them is by the molecular geometry, meaning the way the bonds are actually oriented. The other is by the electron geometry. We'll talk about both of these terms in a bit. But electron geometry represents the positioning of the electron pairs around the central atom. Not necessarily where the bonds are, but where the pairs are. Pairs are also in the bonds, and also they're by themselves, and lone pairs. But basically, the way these molecules are arranged is by these main postulate, this main one, this in bold, that the structure around a given atom is determined principally by the minimizing the electron pair repulsion. So we don't want electron pairs next to each other. We don't want electron groups next to each other. So that's a key concept. Now, there's 2 ways of determining the configuration. The first one is molecular geometry. 3-dimensional arrangement of the molecules in an atom. Very simple. If you have a molecule in a ball and stick model that looks like this, it's bent. If you have a molecule that looks like this, imagine that in 3 dimensions, it's tetrahedral. If you have like this, oh wait, that's also tetrahedral. That one. That's going to be trigonal planar, meaning it's all going to be like, it's like a tripod, but if you flatten it out. There's ones with 5 that are called trigonal bipyramidal, or trigonal pyramidal, or trigonal bipyramidal. It'll be like a tripod with 2 antennae on it, facing opposite ways. And then there's going to be octahedral after that. But we have a whole chart. I'll talk about a whole chart. That's one way. Molecular geometry, the way the molecule is written. Then we have a second way called the electron geometry. So you notice it's not about molecule anymore. It's about electron. So the 3-dimensional arrangement of the electron pairs, both bonding and non-bonding pairs. So for example, if let's say we have NH3, how many electron groups or electron pairs does it have? Did you say 4? Oh, 4. So 4. So nitrogen, in this case, has 1 bond here, 2 bond, 3 bond, lone pair, which is 4. So the way we can, I don't like, okay. Again, with terms, there's a lot of terms. I don't like the way they say electron pairs. It really should say electron groups. So change that, and I'll define groups. So electron groups. So for electron geometry, so electron, I'll put E group. An electron group, so the geometry is determined by how many electron groups are on the central atom. On central. So what determines an electron group? An electron group could be a lone pair. Electron group could be a single bond. An electron group could be a double bond. And an electron group could be a triple bond. So all of those things count equally as electron groups. A triple bond happens to have 3 pairs of electrons in it, 6 electrons. But since it's going in the one direction, it's being bound with between 2 atoms and it's going into one line, it's considered to be one electron group. So this is what we mean by electron groups. It could either be a lone pair, a single bond, a double bond, or a triple bond. So the number of these electron groups directly determines the electron geometry, which makes it easy because if there's 1 electron group, well, then it's really no geometry. If there's 2 electron groups, that means it's called linear. If there's 3, it's called trigonal planar. If there's 4, it's called tetrahedral. If there's 5, trigonal pyramidal. No, trigonal bipyramidal. If there's 6, octahedral. So there's names for each shape of electron geometry based on the number of electron groups on the central atom. It's not too bad. And yes, you have to memorize them. But for molecular geometry, it's a little bit harder. So does everyone understand electron geometry? Before we get into the chart. Any questions on it? Anybody online? Anybody? Any questions on what I just said? No? All right. So molecular geometry, make another slide. So the molecular geometry, put molecular, so what it does is it takes into account lone pair electron repulsion. It's important. So it takes into account the lone pair repulsion. Okay. So what that means is for a molecule like NH3, what actually happens in the 3-dimensional shape of the molecule, meaning the molecular geometry, is these 2 lone pair electrons are very repulsive. Lone pairs of electrons do not like to be near any other electron group, including bonds. So what will happen is they will actually push the bonds away from them. So the electron pair will push the bonds. What that does, oh, here's my email. What that does is it squeezes the bonds a little bit closer together, thus making them look like this. Imagine this in 3 dimensions. This one's coming out towards you. So that's what this means. Molecular geometry takes this into account. So this new shape, this molecular geometry has a name when you have 1 lone pair and 3 bonded pairs that are being squished. This is called trigonal, pyramidal. Pyramidal. I could spell, maybe. Trigonal pyramidal. And that's just one of them. There's a bunch. So you see how it makes a tripod with a little like electron on the top with 2 electrons? It basically does that. It makes a tripod. It squeezes them down. Same thing happens with water. So for water, we have 2 electron pairs. Let's say Mickey Mouse. So it's 2 electron pairs. And these electron pairs push down on the water, on the hydrogen. And they make a bent molecule. And bent is the official term for something that has lone pairs and 2 attachments that the lone pairs squish against. So this is all based on physics. It all makes sense. Okay, any questions? Now we're gonna get to the chart so we can like summarize everything. All the different names. All right. So we're in a chart. Is a chart. Okay. So we'll do one at a time. First thing, if you have something like CO2, where you have a central atom, let's look over here on the right. So a central atom, and then 2 no lone pairs, and then 2 things attached to it. The thing is, don't look at your, okay, so we're only looking at the central atom here. We're not looking at the attachments and how many lone pairs they have. We're just looking at the central atom. That determines where the other ones are oriented. So if we have just a central atom with 2 attachments, no lone pairs, this is called a linear. This is called linear. The electron geometry is linear. The molecular geometry is linear. Because it's in that shape and there's no other electron pairs to push them down or to give it any other name. Okay, next one is when there's 3 electron groups and all of them are bonds. So you have all bonds. It could be single bonds, double bonds, or triple bonds, but they're all bonds. They will arrange equal and opposite to trigonal planar. Make sense? Trigonal, so I guess these are just things you need to memorize. So trigonal planar, when there's no electron pairs. Now we're going to introduce electron pairs. What happens when you have something like this, SO2? You have 2 electrons that are lone, or 1 lone pair on the central atom, and then 2 electron groups coming off of it, 2 bonds. The electron geometry, remember, just takes into the account how many electron groups are on the central atom. How many are there on the central atom in this case? 3, good. There's the lone pair, the double bond, and the single bond. If there's 3, it's trigonal planar all the time. This one has 3, the BCl3, but they're all bonds. Still trigonal planar. So if you have 3 electron groups, doesn't matter what they are, trigonal planar. But now that we have the lone pair, it does affect the molecular geometry, which makes it the harder one to know. Because this lone pair, like we said, just like with water, will push down on the bonds, making it into a bent shape. The angles you're not going to have to know except for the easy ones. The easy ones, I mean, linear is 180, trigonal planar is 120, bent, you can imagine, is less than 120. And then an important one actually is tetrahedral, is 109.5. Everything else you don't really need to know. Does that make sense up until that point? Do you know why this is bent? Because the electron groups are always pushing down. Okay, so again, maybe watch this video over again and go through multiple times to get to know this. Next one. 4 electron groups and they're all bonds. So 4 electron groups, just like methane, they're all bonds. Therefore, the electron geometry is what we call tetrahedral, meaning there's 4 electron groups. Molecular geometry is also tetrahedral because in 3-dimensional space, all the electron groups are bonded to atoms and they're tetrahedral. So now let's take away one of those bonded atoms and we'll stuff in a lone pair, like NH3, like PH3. The electron geometry will still be tetrahedral because the electron group number did not change. There's still 4, but now only 3 of them are bonds. 1 of them is a lone pair. But the molecular geometry changes because as soon as you add that lone pair, you get squishing. When you get that squishing, you get trigonal pyramidal for the molecular geometry. So it's good to not only memorize these terms, but think about it in terms of their shape and what are the lone pairs doing to the shape. They're squishing it. They're squishing the atoms closer together. Okay, next one. Move this out of the way. Next one is, let's say you take away another atom, right? And you have two lone pairs, two atoms attached. Electron geometry, no different. Still be tetrahedral because you have two lone pairs and two atoms bound for a total of 4 electron groups. But now that second pair of electrons will also bend the structure. And it'll bend it even more, which is why the angle is a lot less than 109. It varies, though. That's why they say that. So this is now called bent also, just like we saw when we had one electron pair of one lone pair of electrons with 2 bonds. We saw it bend. Now we're going to see it bend more with 2 pairs. And this is basically what water is like. And it's called bent for molecular geometry. Okay, I'll let people write that down. Any questions on that before we go to the next slide where there's more? Yes, so, oh, it's actually, yeah, so, okay, so this is called, I didn't even tell you, this is called the VSEPR model. So this is spelt wrong. It's VSEPR model. And Logan, you have to memorize all these for the exam. You have to understand, you have to know them. Yeah, I hate the word memorize. You have to conceptualize them and understand them. That's why flashcards, great idea. Practice examples, great idea. I will give you a practice worksheet. That's something I should do. I'll give you a practice worksheet on the shapes. And knowing the difference between electron geometry and molecular geometry and a few of the terms, such as linear, trigonal planar, tetrahedral, and then we're going to cover the next couple. Knowing the terms for electron geometry and molecular geometry should make it a bit easier. So let's cover the rest just for the video's sake, and then I will write a little chart. What is it? Oh, I put this in here manually. Okay. All right, so hopefully you can still see that. Oh yeah, you guys are fine. All right, so next one. What if you have 5 things attached? So you have PCl5. The electron geometry is called trigonal bipyramidal. So it's like you have trigonal, which is 3, bipyramid, 2 more things, 5 things total. The molecular geometry is the same. So basically, another rule, if you have no electron pairs, no lone pairs, then the molecular and electron geometries will be the same if you have no lone pairs, because there's going to be no pushing the bonds. The molecular geometry is also trigonal pyramidal. Now, systematically, let's take one atom out. Take one of the Cl's out, replace it with a lone pair. You get CF4, for example, where you have 4 things bound and 1 lone pair. The electron geometry is still trigonal pyramidal because we don't care for electron geometry, whether it's a lone pair or a bond. But the molecular geometry changes, and it's called seesaw. Now, honestly, this one should be lower on your priority list to know because it doesn't come up often, but it still is a thing, seesaw. And you can see over here 3-dimensionally how it's arranged like a seesaw, where you have, it's basically linear and bent put together. So you have, these 2 are linear from each other, but the other ones are kind of bent on an angle. So it kind of makes a seesaw. Very scientific names, I know. Next one is, let's take away another element, another atom, and put in another lone pair. So electron geometry, still trigonal pyramidal or bipyramidal. And then you end up with T-shaped. So with T-shaped, these electron pairs will now bend the structure even more in such a 3-dimensional way that it will end up like a T. So yeah, that's T-shaped. Another one, low priority list. So I'll put that as like an asterisk, as like they're not, you should memorize the other ones first, I would say. Definitely the ones in the previous slide, very important. But these ones are still, you may see them, but less important. Next one, let's take away another atom and we'll put in a third lone pair electron. Again, trigonal bipyramidal. But here's where something interesting happens. You actually get linear again. It's crazy. But what happens if you see this diagram over here with the XeF2, the three lone pairs of electrons kind of, if you're looking like, if you're looking linearly, like let's say this, if you're looking at my, well, you guys are in the classroom, but let's say this pen is the linear part, is the XeF2, F1, F2. The electrons, the three pairs of electrons are kind of like this. One's going here, one's going here, and one's going down. They're equally distant from each other in this plane. So what that's doing is it's kind of buffering and pushing the atoms. Instead of going bent in certain ways, they're going straight across. It's kind of canceling out the bending in one direction and the bending in the other direction to go straight. So that's why it's linear. Again, that's another low priority one. I mean, linear in general, you should know, but linear in this specific case is low priority because it doesn't come up much. Where you have three lone pairs and then two bonded pairs, that violates the octet rule. So it's not going to come up too much. Okay, the next one is when you have 6 things. So when you have 6 electron groups, they're called octahedral. Professor, I thought octa was 8. It is, but I don't know why they call it that. I honestly don't. It's called octahedral. Whatever. So anyway, when you have no electron pairs and 6 things attached, like you have an SF6, the molecular geometry is also called octahedral. Then we'll do the systematic breakdown. We'll take one atom out, put in a lone pair. We get another low priority one called square pyramidal. So what this does is it makes a pyramid with four corners, and then one's going straight up. So it's pyramid. So it's a square pyramid, but there's one coming up. So it's 5 atoms. And the electron pair, the one electron pair is causing them all the 4 to bend. Then the last case is when you take away another atom and then you put in another lone pair and you get square planar. This one's an easy one. I'll put square pyramidal is another, you don't have to really, is another low priority. Square planar is a low priority also, but it's not that hard because when you have the 2 lone pairs and then the 4 atoms, you get this effect, kind of like the linear effect we saw up here, where the lone pairs of electrons are gonna counter each other, and everything's gonna end up being on the same plane. So, yeah. Okay, that's a lot of stuff, I know. Any questions on that? I want to make it easier for you. Any questions online? Okay, so here's what I'm going to do to make it easier. I'm going to write words. I'm going to chart. So for electron geometry, I'll write E, G, and then M, G. I'll write words. So electron geometry, the only terms you need to know are linear, which means there's 2 groups, trigonal, planar, not pyramidal, trigonal planar, which means there's 3 groups, tetrahedral, which means there's 4, trigonal, bipyramidal, that means there's 5, and octahedral, that means there's 6. Okay, So that's the easy one. That's for electron geometry. That is just the electron groups. So this is electron groups. Now for molecular geometry, there's a bunch. So I'll write them in order of amount. So you're going to have the simplest one is going to be linear. Then if you have linear with lone pairs, you get bent. I'm not going to put these in any kind of, I'm going to put them in increasing order, but I'm not going to put them in like a, I'm doing this off the cuff. I'm not making like a cool chart or anything. So then you have bent. Then if you have three things with no lone pairs, you're going to have trigonal planar. Trigonal planar. Then if you have three things with one lone pair, new term, trigonal pyramidal. Then if you have that covers most of them. Then you're going to have, let me see. See, even I forget without looking at the chart. So trigonal pyramidal, that covers all those. Then you have bent, you had that already. Then you get into wait, what did I just see? Yeah, I'm trying to put them in importance order. Then you octahedral. So trigonal, then you have trigonal bipyramidal, sorry. Trigonal, which is 5, trigonal bipyramidal. Then you're going to have, oh no, bipyramidal. Then you're going to have octahedral. And then low priority ones, we'll write seesaw, T-shaped, and square planar, and square pyramidal. So these are just terms. Like if you just want all the terms in one place, there they are. But the charts are actually the best way. If like taking a look at this chart, listening to me explain it in the video, that's the best way to do it. And then doing problems. Okay. Any questions on that? You guys are beat probably. Let's see what we have to do left. Okay, molecular structure. So basically what the end goal of this is to draw the Lewis structure, be able to determine the shape, either both electron and molecular geometry, and then that's it. So rules, okay, yeah. Everything else is basically we covered already. And then you'd also be able to figure out polarity from this. So that's another thing. So knowing the shapes, it gives you another perspective on polarity. Because something like NH3, or which of the molecules is polar, I'll just give you NF3. So if you do NF3, it has an electron pair. Now we know a lot about these lone pairs. This lone pair is going to push down on them. So now the nitrogen is going to be, it's going to look like that. And the molecular geometry is going to be what? Do you remember? With 3 facing down and then 1 lone pair? Think camera. Where's the camera? Trigonal. Good, trigonal pyramidal, not bipyramidal, just 1. So trigonal pyramidal, good. And online, nice, awesome, Isaiah. So trigonal pyramidal. So if it's trigonal pyramidal, and we're putting in the concept of polarity in here, meaning electronegativity differences, there is an electronegativity difference, a big one, between nitrogen and fluorine. But now we know it's not symmetrical anymore. So you're going to have an unequal pull of electrons in the direction of fluorine, meaning this molecule is polar. But if you didn't know what the electrons do, you would say, oh, look, they pull all in the opposite direction. It's nonpolar. But no, we know better than that now. So does that make sense? Yeah, so that we can use this VSEPR model for polarity, to figure out polarity. Yeah? Okay. All right, so we'll do one more. So well, we just kind of saw the answer, whatever. So here, I'll do this. So what type of structure does XeOF2 molecule have? So that's weird. So which one's going to be in the middle? What do you think? So not oxygen, despite the way it's written, Xe is going to be in the middle because it likes to, I don't know, it's not really a good explanation for that. I just know it's in the middle. Usually the noble gases, if they are forcing to be bound to something, they're in the middle. Yeah. What? Yeah. Yeah, okay. It's because it doesn't want to bond to anything. It's being forced. Yeah. So then you have the fluorines. So you have, this is going to have 8 total. So we're going to have 1. Wait, what am I doing? So hold on. I'm starving, by the way. 1, 2. I'm not as sharp when I'm hungry. You're not you when you're hungry. All right. So the fluorines are going to make single bonds. The oxygen will make a single bond because, well, it wants to be satisfied. But either way, its octet rule is good, and we don't want to piss off the xenon. So, well, actually, it's probably going to make a double bond because then we'll have a lone electron. So it's going to make a double bond. So what's going to happen here is you'll have, after it's said and done, you're going to have how many pairs of electrons around the xenon? You have 1, 2, these lone pairs. And you're going to have 3 things that are bound to it, 3 atoms. So let's go back to our chart. You have 3 things bound to it and 2 lone pairs. Oh, look at that. So we know it's trigonal pyramidal or trigonal bipyramidal on the electron geometry because we have, there we go. No. Yeah. So we know it's trigonal pyramidal, bipyramidal based on electron geometry because you have 1 lone pair. I guess I'll circle these, 2 lone pair. Then you have the 3rd electron group, 4th electron group, 5th electron group. But for the molecular geometry, these 2 electron groups are kind of pushing these away to make it into a T shape. So that's why T shape would be your answer. Yes, that's the answer. Okay. All right. Any questions on that? Oh, what am I doing? Here we go. Any questions on that? So any questions on how I got the Lewis structure for that? That's a difficult one. So the idea was that I filled in xenon first as 8, because we know it has 8. And then we put the fluorines and the oxygen around. Now we know oxygen wants to get the octet rule. So even if it has 6 electrons, and then if it makes 1 bond, it's not going to get the octet rule. So right now it has 1, 2, 3, 4, 5, 6, wait, 1, 2, 3, 4, 5, 6, 7 electrons. So it needs to make its 2nd bond. And then the fluorines make 1 bond to make their octet. Now, if we left this 1 bond, remember I said before that we don't want to piss off the xenon because we want to always, if we need to make only 1 bond, we'll do 1 bond, never usually more than 1. In this case, that wouldn't work because if you had only one bond, what will happen is in the xenon, you'll have an uneven, an odd number of electrons. In this case, you'll have 1, 2, 3, 4, 5 electrons. That's really not good. That's a radical. So a radical means when you have one lone electron, and that is extremely reactive with really anything. So we want to avoid that at all costs.